Hello everyone and welcome to a new tutorial on the channel. Today we will talk about the nodal analysis. Nodal analysis is an important method and technique to solve circuits. Actually, I find the nodal analysis is very easy and it's very helpful. So first of all, today we'll talk about the nodal analysis explanation and the basics of the nodal analysis. Then we will move on to something called the shortcut method. Actually, this shortcut method is obtained when you solve a lot of circuits using the nodal analysis. Then you will find a way that you can use a shortcut to solve it using the nodal analysis. Actually, it will save a lot of time. Then we'll talk about a supernode. Supernode is very important and it's very easy, by the way. It's very easy. A lot of people find it's very difficult, but I personally feel it very easy, and we will see why it's easy. And finally, I will give you some practice examples with the answers, so you can solve it and practice on it later on. So I feel like that. Okay, let's start. Okay, so first of all, before we start solving nodal analysis problems, we have to understand what kind of nodes we have. We have two kinds of nodes. First, we have a reference node and we have a non-reference node. The reference node, also known as the ground, and the ground we most commonly we refer to the ground with this symbol. And the ground is the node that has the most branches. So in all circuits, there will be a node that has the most branches. If there is two nodes with most branches, so one of them will be ground and the other one will be a non-reference node. So the non-reference node will be any node that is not the ground. So in any circuit there will be only one ground. You cannot have two grounds, okay? And the voltage in these grounds, we by convention we say that the voltage in these grounds is 0 volts, okay? So the voltage in the grounds is 0 volts, and the voltages is in these non-reference nodes. We put it as unknowns. So there is voltage, okay? There is voltage. So when I give you a circuit and I ask you to find the voltages in the nodes, you don't have to find the voltage in the ground because it's 0. It's already found by convention. So you will have to find the voltages in these non-reference nodes, and we will find that very easily in the next examples. But first, before I go to the examples, we have to know that I should make sure that all of you understand that the nodal analysis is based on the KCL, which is the Kirchhoff current law. So it's very easy, Kirchhoff current law, and we will also find out, if you don't know the Kirchhoff current law, you can understand the nodal analysis with the examples, with the next examples. But to make the nodal analysis more understandable, I will give you this circuit. If I ask you to find the current passing here, do you have to find the nodal analysis? No, you don't have, because a circuit like this is very simple. Using Ohm's law, the current is equals to 10 over 2 is equal to 5 amps, which is the voltage over the resistance will gives you the current. Okay, so directly using Ohm's law, you can find the current. Also in a circuit like this, if you wish to find the current passing here, how you find it? First of all, you have to take these two resistances in parallel. You will have three series with 2, you will have 5, so it will be 15 as a battery with what? With 5 ohm in next to it. So the current passing here, which is this current, is same as this one because I didn't change, which is the current which is out of the battery. Okay, so this also is the current out of the battery. So these two currents are the same. So using Ohm's law again, 15 over 5, which is equal to 3 amps. So the current is equal to equals to 3 amps. So in a circuit also like this one here, you don't have to find or use nodal analysis. And just all about saving time. As engineers, we always tend to save time. We don't have to go for the most difficult way than we have, while we can find it in an easy way. So now I will give you a circuit like this. In this circuit, you cannot, if I ask you, for example, to find the voltage in this 2 ohm resistance, you cannot find it using Ohm's law. For example, you cannot find the current passing here, then you will take the current multiplying by the resistance gives you the voltage, because you don't know how much the current goes here. You can say that I can't find the current because here I have 2 volts and here I have 4 and 2. 4 and 2 is equal to 6. 2 over 6. No, this is not going right, because this 2 is not series with this 4. And also it's not parallel, because here you have resistance and here you have a battery. If it was only resistance, I will be using same as this technique. But it's not only resistance. Here I have a battery, so I cannot cancel this battery or take it parallel or any of this stuff. So in this case, you have to do the nodal analysis. You have to understand, guys, that this node is the ground. Why I said that this node is the ground? Because it has the most branches. Here it has 1, 2, 3. Okay. You can also say that this node will be the ground because it has 1, 2, 3 branches. I will say that you are correct. This one can also be the ground. Then this one will be the node. If you said that this one is the ground and this one is the node, this is correct. So one of them will be 0 volt and one of them will be the unknown voltage. Okay, so that it is like this. It's like a circle that we are looping on. So it's okay if you said that this one is the ground or this one is the ground, because one will be the ground and the other one will be the node. Because you remember, you cannot have 2 grounds in one circuit. So if I assume that this one, if I assume that this one is the ground, okay, the voltage here is equal to the voltage here, which is the node voltage. Okay, it's the same. If I just put the V here, this node voltage is it's equal to this voltage, because it's linked. It's one node. So the node, it starts from here and ends to here. Okay, this is the node. So that's it. So you can easily find the voltage in the node, and in this area, if you know that this voltage is equal to the nodal voltage. So in this case, what you do, you just apply the Kirchhoff current law. So you will say that the current, you will do Kirchhoff current law in this node. Okay, so here is the battery. The current will go here and comes here. Let's say that this is I1, and also here's a battery, and the current comes here and goes to here. This is I2, and I will assume, just an assumption. I can also say that the current comes from here to here, but as assumption, I will say that the current will come from here to here, from top to down, and this one is I3. Using Kirchhoff current law, I will have that I3, it's equal to I1 plus I2, because I2 and I1 are entering the node while I3 is leaving the node. So the leaving currents equals to the entering currents. This is the Kirchhoff current law. How easy it is, right? The entering currents equals to the leaving currents. So now I will substitute these values of currents. I3 is equal to what? I3 is equal to the voltage here minus the voltage here divided by the resistance in between. So I3 is equal to V, which is the unknown, minus the voltage here, which we assumed at the beginning that the ground is equal to 0, all divided by the resistance in between them, which is 2. That's equal to I1. I1 is equal to the voltage here minus this one over this one. It was equal to 2 minus V over 4 plus the voltage here, which is, look at the arrow. The arrow starts from here, ends to here. So 8 minus V. Okay, don't say V minus 8. No, we're not going from left to right or from right to left. No, we are just following the arrow. Because if you just change the arrow, that I2 will not be here. It will be on the opposite side. It will be leaving the node. It will not be entering the node. So just matter of mathematics, and you will find that always it leads the same way. So we can say that I2 equals to V, or 8, minus V, all divided by 4. And you can start, or you can just multiply all the equation by 4. You will find that here is 2V is equal to 4 with 4 cancels, 2 minus V, 4 with 4 cancels, so it will be 8 minus V. Here I have 2V minus 2V, I will put it there to be 4V. It equals to 2 plus 8 which is 10. So 10 equals to 4. So that the V divide both sides in 4, it will be equal to 2.5 volts. So the voltage here, it's equal to 2.5 volts, which is equal to this voltage, which is equal to this voltage, okay? Now we move to a bigger problem, and this one is not difficult because this one has current sources instead of voltage sources. And when we have when we have current sources, actually it's much easier because when we use KCL, we substitute the currents. For example, if I have like this as the previous one, I1 equals to I2 plus I3. Here I have a current source, then I will substitute the value of this current source directly. I don't have to apply the Ohm's law instead of to put V over R. So directly in this case, you can use the current that you have. So, for example, this problem, like the ground obviously is this one. For those who are asking why, because this node has the most branches. So here, 1, 2, 3, 4, 5. Okay, it has more branches than compared to any other one. So, if I just name this one V1, and this one is V2, and this one is V3, okay? And V1, an entering current, this one is an entering. Here we assume that this one is leaving, and we assume that for this one we are not assuming because we see it's leaving because the arrow here is leaving out, okay? So we don't have to assume anything here. We just assume in these cases where there is no current source. And we can also always we can assume in the opposite direction. If you want to assume it like this, then we have no problem because it will be 0 minus V1. If I use the arrow down, it will be V1 minus 0, okay? And if I use the arrow up, it will be 0 minus V1. So it's all the same, okay? Now let's start. For V1, I can say that 5 is entering equals to the leaving ones, which is 2 is leaving, plus V1 minus 0 divided by 2. And this one will be equation A. Okay? And for V2, 2 is entering, and assume this one is leaving, and assume that this one is leaving too. Okay? And actually, before I continue, V2 and V3 have the same voltage. These two nodes have the same voltage. Ask me why, because there is no element. If there was a resistance here, I will say that there is a voltage drop here. Because now, these two, the 4 and 4 resistances are just parallel to each other. So I can just cancel them both, and I can put one resistance, which is equal to 4, parallel with 4, which is equal to 2. So this one will be 2 ohms, I'm sorry. Okay, so you can assume that too also. You can put 2 ohms here. Or you still can stay with the previous one, 4 parallel with 4. Then you will find out these two resistances have the same voltage. But staying with this one is much easier. So we cancel this nodes. We have 2 nodes, not 3 nodes. So the V2 node is here. Okay. So if I said that here is 5, this is the first equation done. And the second equation, I say that the 2 is entering, and this current is leaving, and this one is leaving too. So I will say that the 2 is entering equals to V2 minus 0, all divided by 2 ohms, plus the other one, which is leaving, which is 1 amp. And let's say that this one is equation B. I know that all of you should know how to solve two equation system. And actually, it's very easy. It's not difficult at all. So you can just substitute these two equations and solve it for the two unknowns, which is V1 and V2. Then boom, you have your unknown, which is V1 and V2. And let me know in the comments down below what are V1 and V2. I'm sorry, V1 and V2. Now let's go for the shortcut method. The shortcut method actually it's the one that I prefer actually. So if I just have this problem, it's actually similar to the previous one and that we did above, but this one is 12 volts, not 2 volts. So it's very easy. Actually, it's very easy. The shortcut method that I say, actually, it is the voltage, which is the unknown that I'm seeking for, multiplied by the summation of 1 over the adjacent resistances, minus, and this minus should be distributed, okay? And this minus should be distributed along all the summation. So the summation will be the sum of the negatives, okay? Minus the summation of the mutual voltages divided by the resistances of these mutual voltages, okay? That's all equals to the sum of the currents in that particular node. So if I have, you will find it confusing actually when I say it from here, but you will find it more easy when I start to solve it. So if I just have this node here, and the voltage here is unknown, okay? If this voltage is unknown, I can find it easily using this shortcut method. So I will start saying that V, which is the unknown, let's say that it's Vx, okay? So not to confuse you, it's Vx, okay, which is this part, V, multiplied by the sum of the 1 over the adjacent resistances. How many adjacent resistances I have? I have 1, 2, 3, okay? So multiply by the sum of 1 over 4 plus 1 over 4 plus 1 over 2, okay? Minus, this is the minus, the sum of the voltages, the mutual voltages. Where are the mutual voltages? Which is the voltages next to that node. So here is a mutual voltage and here is a mutual voltage, okay? These are the two mutual voltages. And this mutual voltage has the resistance of this, which is the resistance between it and the required node voltage. And this mutual voltage has a resistance of this, because this is the resistance between this mutual voltage and this required voltage node, okay? And this one actually is 0, so I don't have to say 0 over 2 because 0 over 2 will be 0, so I don't have to pay it attention. So if it is a ground, like in this case, just skip on it to save your time. So the mutual voltage, I will start with the 12 over 4 plus 8 over 4. That all equals to the summation of the current. Is there any current entering this node? When I say current, I know that there is actually a current coming here, but I'm saying like the current sources. So there is not. So I will say 0. There is no current source. If there is a current source here with 2 amps, I will say that there is entering 2. So if I have a 2 amps entering here, and I have 1 amp leaving here, what I will put here? I will put 2 minus 1, the entering as positive and the leaving as negative, okay? But in our case, we don't have any entering or leaving current sources, so I will stuck with the 0. And actually, just don't forget, guys, that this negative will be distributed along all this summation, okay? So you can say that this is the negative summation, okay? And don't put inside negative, so don't put here negative, because when we distribute the negative, this one will be positive. So no, so it is positive in the actually it's positive, but there is a negative will be distributed, okay? So solving this problem now was very easy. We see how a quarter and a half, so it's 1 multiplied by Vx minus 12 over 4, which is 3, and 8 over 4, which is 2, so 3 plus 2, which is 5, minus multiplied by 5, which will be minus 5, which is equal to 0. I will just move it there, so 3x is equal to 5 volts. You see how fast I solved this one? So this shortcut method actually is very relaxing, and I just feel it's better than the actual method. I personally solve all nodal analysis problems using this technique. Here I have another problem. It's similar to the one that I've solved before. I can also solve it using the shortcut method. So I will solve it quickly. So here is the ground, and here is V1, and here is V2, and here is V3. Okay. V1, you don't have to find V1. Why? Because V1 is parallel here, so here is no resistance. If here is a resistance, I will say that there is a voltage drop here and V1 will be different. But here is no resistance. So when there is no resistance, that means this voltage is equal to this voltage because they are parallel. So V1 is equal to 5 volts. So now you have solved one node. You have only two nodes left. So in node 2, I will say that V2, I will use the shortcut method here, okay? V2 multiplied by the summation of the adjacent resistances, this one and this one. Don't forget 1 over resistance, so it's the conduction, which is in Siemens. 1 over 3 plus 1 over 4 minus the mutual voltages. Here the mutual voltage is 5, so 5 over 3, this 3. Here the mutual voltage is 0, so you don't have to put 0 over 4. And here the mutual voltage is what? Is V3. But here we know that here is a current source. So here you don't have to put V3. We skip V3 because we have a current source here. So in this case, what we do, we just stop putting the mutual and we start put the equal sign and we move to this area of the equation directly. So, and the sum of the current, which is leaving minus 2, leaving 2 amps. This is equation A. Okay, this is equation A. And now moving on to another equation, which is this one, V3 and brackets. And first of all, I have the adjacent resistances, so it's 1 over 5 plus 1 over 2 minus the mutual voltages, 6 over 5. Here is 0, skip. Here I have a current source, so that's equal to 2 entering, so it will be positive 2 here, positive 2. So this is equation B. Solving these two equations will be very easy and it will give you the answer. Solving this equation separately will give you V2. Solving this equation separately will give you V3. So these two are not system, okay? These two equations are not a system. Sometimes in circuits you will be stunned and surprised that the two equations have no relation to each other. So you can solve this one separately and you will have V2, and you can solve this one separately too to have V3. And I will just save time and will let you guys solve it. You can pause the video and solve it. Now we will move on to the last part of our video, which is the supernode. If I told you that you have this circuit and I want you to solve it using the nodal analysis, how you will solve it? You will say directly that this one is the ground because it has 4 branches, and this one is V1, and this one is V2. That's perfect. But you will be stunned that there is a voltage source here. So this voltage source, if we say that this voltage is 5 volts, so V2 will be 5 volts or V1 will be 5 volts. You can pause the video now and think of it if you want to. But the actual answer is none of these two is correct. Neither of this is correct, nor this one is correct. None of them will be 5 volts. Actually, this is a supernode. That's what we call a supernode. So a supernode, by definition, when you have a voltage source between two non-reference nodes. That's why I have explained the reference node and non-reference node. So if you have a voltage source like this one here between two non-reference nodes, this one is non-reference, this one is non-reference, this one is reference. So if I have a voltage source here, this voltage source will be between a reference node and non-reference node. I'm sorry, between a non-reference node and a reference node. So this one is not a supernode because this one is not between two non-reference nodes. But this one, the 5 volts that I have here in this case, is between this one, and these two are non-reference node. So in this case, they can create what we call a supernode. Actually, in my opinion, I feel like the supernode is easy and can make the problem for me easier because in a supernode, I use only one equation. It's like I'm mixing between these two nodes. These two nodes are like merged. I can say merged together. So I will give an example and you will see that what I'm saying is very easy. Okay, so let's solve this one by giving it a number. So let's say that this one is 2 amps and this one is 1 amp, this one is 2 ohms, this one is 3 ohms, this one is 5 volts as it is, and this one is 4 ohms. Okay, so now if I want to solve this one whether using the normal nodal analysis or using the nodal analysis shortcut method, both of them are correct, but for me I prefer the shortcut method. So I will start with V1. So in the supernode, actually we put all the both nodes that made the supernode in one equation. So now V1 and V2, both these nodes made the supernode, so I will use them both. So I will say first that V1, the mutual resistance of it is 1/3. Is there any other mutual voltage? No, here is a current source, and this one is a supernode. In the supernode, I don't go forward, I will stop here. Here is a current source, so there is no voltage. Then I will move on to V2. I will put V2 also in the same equation as V1, plus. When I start with V1, I will separate them with plus. V2 multiplied by the resistance, which is 1/4. Is there any mutual resistance or mutual voltages? No. So I will say 1/4 and I will stop. Then I will say equal to the current entering the supernode. The supernode actually is all this is a supernode. So this one is entering and this one is also entering the supernode. So the supernode starts from here and ends to here, okay? So both are correct. So we have entering current 1 amp, and also this one is entering, so 2 amps. If I just reverse this one, I made it down, it will be -2 amp, okay? But since this one is up, that means it's entering, it will be plus. So entering as plus, leaving as negative. So that's it. This is our equation A. A lot of you will say how you would solve two unknowns. This is V2, okay guys? How you would solve two unknowns in one equation. Mathematically, this is impossible. So I will give you another equation. How to give the other equation? Giving the other equation will be by KVL, which is Kirchhoff voltage law. I will make a loop in the supernode. Then you have your second equation. I just before said that since this one is V1, that means also this one is V1. And this one is V2, that means this one is also V2 across the resistance, of course. So you can go for a loop. You will say entering as a negative minus V1 minus 5 volts plus V2 is equal to 0. Entering from here, negative V1 here, negative 5 volts here, positive V2, okay? And this one, of course, is 0, so I don't give it attention. Now you have your B equation. Solving these two equations in a system will give you V1 and will give you V2. Then you just solve the problem very easily. And also, you can give me in the comments down below the values of V1 and V2, as I will save time and I will skip it, okay? I think that Supernode is easy, but you just have to solve more problems and it will be easier for you. And here, I just put another problem concerning Supernode. So this one will be the ground, of course, and this one will be, since this voltage source is between two non-reference nodes here and here, this one is a supernode. So this one will be V1, this one will be V2, this one will be V3, and yes, 3 nodes. Here it's not a node because it's connected directly to the voltage source. If I just want to say here is V4, I will directly say that V4 is equal to 10 volts. So you don't have to confuse yourself with more nodes. Directly 3 nodes is enough. Solving this one will be easy too, just like I told you. You can start with V1, saying that V1 is not supernode, so we will solve it as we used to solve it previously. V1, say 1 over 5 plus 1 over 2. These are the adjacent resistances to V1, minus the mutual voltage, which is V2, minus V2 divided the resistance between V1 and V2, which is 2. Is there any mutual voltage? No. That equals to the current, which is 3. 3 is entering or leaving. Since 3 is entering, it will be positive 3. This is equation A. Now moving on to V2. We know that directly when we start taking V2 or start taking V3, we will know this one is a supernode, so you will take both as a supernode, okay? So we will say V2 multiplied by the resistances, 1 over the summation of the resistances, so it will be 1 over 2 plus 1 over 7 minus the mutual voltage, which is V1, over the resistance between them, which is 2. That's it. Just like I told you, don't exceed the supernode. Now we move on to V3. Just like I told you, put plus, okay? Plus V3 multiplied by the resistances, which is 1 over 2 plus 1 over 5, which are these two, okay? Minus the mutual voltage, which is 10, and the resistance between 10 and V3, which is 2. And that is equal to, is there is any current leaving or entering all supernode, okay? All supernode, not only V3 or only V2, because this equation concerning all supernode. So is there any current entering or leaving this supernode? No. There's no current source entering or leaving, so it's 0. And this one is equation B. And also, as we know, we have 3 unknowns, V1, V2, and V3. How we can solve 3 unknowns with 2 equations? Just like I told you, mathematically it's impossible, so we have to obtain a third equation using KVL, okay? Here. So this one will be plus negative V2, and here will be plus negative V3. Moving along the loop, minus V2 plus 3 plus V3. So minus V2 plus 3 minus, plus again, V3, this is equal to 0. And this is equation C. Now we have equation 1, 2, 3. Solve it using a system. You will have the value of V1, V2, and V3. Some people solve it using MATLAB. Some solving it using Gaussian elimination. Some use, there are a lot of techniques actually you can solve a metric system. Actually, there are a lot of websites to solve this metric system if you want to, and solve the equation systems. So you can just open them online, put your 3 equations, they will give you back the 3 unknowns. And that's it for today. But before I conclude and end up the video, I just put practice problems from our reference book, the Fundamentals of Electric Circuit, the 5th edition, written by Edison or Edwards, I forgot his name. But this book is very, 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 very good actually, and there are a lot of examples you can practice. So exactly as this one, this is a practice problem. They're obtaining the voltage nodes, which is this one and this one, and you just put the answer. So you can solve these problems and check whether your answer is correct or not. And actually, I just put four examples between a supernode and not a normal nodal analysis problem. So actually, I will upload this file and I will put it in the comments down below. So don't forget to download it and practice these problems because they are beneficial. And I believe that watching videos only will not make any benefit. Solving the problems after watching videos and watching tutorials will be that beneficial. And hopefully we meet, guys, in another tutorial. Hopefully you just joined the tutorial, and write me in the comments any feedback, any things that you want me to edit or change or to fix, because I'm doing this for you guys. I'm not doing this for me. And hopefully we meet in another tutorial, guys. So study well and see you soon. Goodbye.